So,
Not too bad, yeah.
yeah. Okay, so we're just gonna get started with number 1. So it's really long. Suppose that you are interested in studying the inheritance of 2 traits in garden peas. How do you even say that word? Cotyledon?
Yeah, cotyledon.
Cotyledon color and pod shape. Cotyledon colors can be either yellow or green, and pod shape can be either inflated or constricted. You set up a cross between a true breeding plant with green cotyledons and inflated pods with a true breeding plant with yellow cotyledon and constricted pods. All of the F1 plants have green cotyledons and constricted pods. You then self-fertilize the F1 plants and obtain the following results. And then you have the results right there. So part A, propose a null hypothesis to test in a chi-square analysis. So the way that we did it is we made the conclusion that the green color is dominant to yellow and the constricted shape is dominant to the inflated shape. And you can see that because based on the numbers, the highest amount are coming from the green and the constricted pods. So that's how we ended up with our hypothesis. So for B, basically what we have to do is we wrote out the cross, and I'm just gonna write down the results. So we have green. Can you see that? I hope you can see that. We have green and constricted. That means constricted. Ours, we had 9 out of 16. That were those. We had green that are inflated. I'm just gonna put in flat. So we had 3 out of 16. Yellow, that's yellow. Constricted is 3 out of 16. And then yellow inflated, we have 1 out of 16. So now we have to use the chi. Let me bring this up. We have to use the chi-square equation. So, which is x2 equals the sum of the observed minus the expected squared over the expected. And you have to do that for each category that we have. So basically, we have x squared equals our observed, which is in the handout, 562 minus our expected. So in order to do that, we multiply the ratio that we got by the total amount, which in this case would be total 1,000. Sorry, 1,026.
1,000, yeah.
Our total. So you would multiply. So for example, if you're doing the first one, we would multiply 9/16 times 11/26. That number 633, and then we divide it by the expected as well. And then that would give us, for this section, it would give a total of 796. And you would do this process for each one, and then you would add them all up together. So plus that, plus this one, plus that one, plus that one, plus this one. And then our overall chi value would end up being 43.56. And there may be some rounding issues, but yeah. So this is our answer for B. And then for C, if you compare it to the chi value chart thing, this value ends up being too high or whatever, and it leads us to believe that this hypothesis is incorrect and we reject the hypothesis. And then to form a new hypothesis, we kind of said that it doesn't really follow independent assortment, that it's possibly that it has something to do with being on the chromosome, something like that. And yeah, that's number one. This takes forever. Okay.
For this. It's still going to this. Okay. Okay, so that was number one. So let's go to number two then. Okay, so for two, in mice, the shaker quality or head tremors, whatever it is, I don't know, is thought to be controlled by a gene on the X chromosome. Shaker is little s, recessive to normal s. So for this, I'm going to depict an X chromosome that has a trait. I'll depict it like that. If it doesn't have the trait, like that. So this would have the big S on it. This has the little s on it. So this has the recessive trait. So, and then another gene that's located on, that's an autosomal gene, controls coat pigmentation. So the big B is dominant, and it gives us black coat color, and the little b is recessive, and it gives us white coat color. But if it's heterozygous, so it's like this, then it will give us, what was it?
Black and white.
Yeah, the black and white spots. Yeah, we'll just see spots. It gives black and white spots. Can we read all that? Yes, we can. Okay, perfect. Get back to where it was. Okay, so we got that. So A, based on what we have learned in class, what inheritance pattern best describes the coat pigmentation trait in the mice? So the coat pigmentation. So the coat pigmentation is, oh, did you say codominance? Yeah. So the coat pigmentation is codominance, because if it were not, then the big B would dominate the little b, and the heterozygote genotype would be black, not black and white spots. If it were, let me think, there's codominance and there's incomplete. If it were incomplete dominance, instead of being black and white spots, it would be gray all over. Okay, so now part B. Let's see. Here we go. So determine the genotypes in sorry, let me read this. A true breeding normal or no tremors female is crossed to and she's black, is crossed to a shaker white male. Okay. And then it asks what are the genotypes and phenotypes of the F1 offspring. So these two, the normal black female is crossed to the shaker white male, what would be the genotypes and phenotypes of the offspring. So let's do the cross. Actually, let's use this. It's more fun. Okay. So let's start with the X and Y chromosomes. So for Y, is that for the X and Y? So the male is affected, so he's going to be like that. The female is not affected, so she's going to be like that. We do the cross. So we have that. We have that. We have that. Yeah, and then we have that. So we have males that are normal, and we have females that are carriers for the shaker trait, but they won't show the phenotype. That's for the shaker trait. Now for the black and white trait, we have. Let me see that. Yes, we can. Yes, okay. Let's continue. Okay. Then we have this. Okay, so these will cross like so. So they all will be heterozygous. So they all will be black and white spotted. So you'll have some that will be males that are normal with black and white spots. Some that will be females that are normal but are carriers for the shaker trait. And they will also have black and white spots. Okay. All right, now for next part. A male and a female from the F1 offspring, so the male, the female, are crossed together. You count the number of offspring from each litter, and after several litters of pups, you have observed the following. Then it gives a list of phenotypes, all different possibilities: normal black and white spots, normal white, shaker black, and so on. And it gives the number of each. Then it asks, perform a chi-square analysis to examine the null hypothesis that the shaker gene is X-linked and the coat pigmentation gene is found on an autosome. Okay, so for this one, so let's write down the genotypes first, so we don't forget. Okay, so these are the genotypes of the parents that are being crossed. The F1 parents that are crossing to make an F2 generation. Actually, let's leave that out there, actually. Let's do this. Let's erase some of it, not all of it. Yeah. And then erase that one too. And then, yeah. All right, so this is going to be the F1 cross. So find something like that. And then this would be big B, that'll be big B, that'll be big B, big B, little b, big B, little b, this would be little b, little b. Okay, so this will be the F2 generation. And then it wants us to do a chi-square analysis. So the ratios, okay, let's see. So the ratios are going to be, let's erase this first. Can you see all the way down there? No, you can't. No, we can't. Now we can. Okay. So the ratios, we're going to have, so we don't care about the male or females. We don't care about whether they are male or female. We're only looking at whether they're shaker or not, and their coat pigmentation. So for shaker, there will be, one second. I didn't think of this for a second. This is going to be kind of complicated. So there'll be normal and black. Okay, so normal and black, they will be, So the half of them will be thank you. Yeah, so
Normal and black will be this. Normal spots that.
what, did I miss something? I think I'm missing something here. Hang on one second. What am I missing here? Oh, now I see what I'm missing. Yeah.
You gotta change. Yeah.
Yeah. That's better. Okay. So yeah, so going back to where we were at. So normal, 3/4 will be normal, and then only 3/4 will be black. Yeah. 3/4 will be normal, and 3/4 will be black.
1/4 will be black.
Oh, sorry, because heterozygous, I forgot. Heterozygous is black and white spotted. Yes, thank you. I forgot about that. Yes. So normal and black will be 3/16. Because 3/16 times 1/4 is 3/16. And then we have normal. I'm going to abbreviate this. Normal and spotted. It's going to be 3/4. No, yes, 3/4 times half, which is 3/8. Yeah. So 3 out of 8 will be normal and spotted. And then next we have normal and white. So there'll be 3 that are normal, and 1 that's white. So it's going to be 3/16. So it's like normal and black. Let me write that correctly. Okay. Now next we have shaker. So shaker, there'll only be 1 that's shaker. 1 out of 4 is shaker. So 1/4 is shaker, and black. Black is also only 1/4. So it's going to be shaker and black is 1 out of 16, because 1/4 times 1/4 is 1/16. Next is shaker and spots. So for shaker, we have 1/4 spots is half. So shaker and spots is 1/4 times half.
2/16.
Yeah, 2/16 or 1/8. Yeah. You could say 2/16 or 1/8. It's the same thing either way. Yeah. And then shaker and white. So shaker is only 1/4. White is only 1/4. So it's going to be 1/16. So shaker and white is also 1/16. Okay. So we have our values. These are our expected ratios. And then we got to compare that to the observed ratios. So for the observed, it is, so normal and black is, it's gonna be kind of hard to fit this. Let me abbreviate this so it can all fit. Okay. Normal and black, 3 out of 16. These are the expected values. Expected. And then the observed values will be here. Okay, so for normal and black, we have 3. Normal and spotted is 11. Normal and white is 4. Shaker and black is 3. Shaker and spotted is 5. And shaker and white is 0. Okay. So now, so we have our ratios. You know, we got this. Okay, so now we plug these values into our chi-square table, or a chi-square equation rather. So the way we've got to do this is, so the way we got to do this is, we got to take each one of these values and multiply it by 26. So, in the calculator.
I have all the numbers right here.
Perfect, yeah. So, I'm just gonna do one because it's gonna take forever if I do all of them. So, you take 3 out of 16, and you would multiply it by 26, and you would get 4.875. And do the same thing for this one. 3/8 times 26, which would be 9.75, and so on across all of these. And so now what's the next step? So you take those values, and then you yeah, this is kind of complicated. Wait, 1 second. Okay. Yeah, so we use our chi-square value that Derek used earlier again, which is let's see. So I already wrote all this. So let me. Okay. Yeah. So I'm gonna erase all this. So. Okay. So we use x squared. X squared is our chi-square value, which we're trying to calculate, and we use the that's the sum sign. So it's going to be right. Right. Hang on 1 second. I'm sorry. Okay. Okay. So what you do is you take your observed value, which is 3. You plug it into here for observed. Then you take the expected value, which was 3/16 times 26, which was 4.875, right? So you take the value, multiply by 26, get 4.875, and plug it into here for expected. You plug it into here again for expected. You square this value of observed minus expected. You square it and divide it by the expected, which is 4.875. And you do that again for each one. You do a total of 6 times. And when you do that, you get the answer. That x squared equals 4.77. I think I covered everything. Yes. Okay. So that is our x squared value. So let me come back over here. What was the question again? So yeah, we were just supposed to calculate the x squared value. So we did. Then parts D is interpret the x squared value. So, or rather the chi-square value, I should say. Determine if you should fail to reject or reject the null hypothesis. So we got to use our table we had before in the PowerPoint, and it tells us. So first we have to talk about degrees of freedom. So we have 6 possible phenotype combinations. So we got to use the n-1 value. N is 6, so -1 is 5. So we have 5 degrees of freedom. And then we look at the chart, and for 4.77 under 5 degrees of freedom, our p-value will be between 0.5 and 0.2. So we do not reject our null hypothesis. We fail to reject our null hypothesis. So for now, we say that that the shaker gene is on an X chromosome, and the coat color gene that controls whether you're black or white or black and white spotted is an autosomal gene. Okay, I think I covered it. Okay. Minimize this.
So now we're going to go on to 3, which is talking about Cheshire cats.
Is that from Alice in Wonderland?
Yes.
Yeah.
Is this where this is coming from?
Yes.
Okay.
And so the question says, suppose that you are studying the inheritance of the grin and disappearance traits in a rare breed of Cheshire cat. The grin trait is controlled by a dominant allele for large grin, capital G, and a recessive allele for small grins, or little g. An independently assorting gene controls the disappearance trait and can exist as either a dominant disappearance, capital D allele, or as a recessive non-disappearance allele, little d allele. So we're going to perform a cross where all of the traits are heterozygous. So, can we see up here? Perfect. So big G, little g, big G, little g. There we go. So that'll give us that. Okay. And then we're going to cross the disappearance one as well. So give us big D, little d. So it'll give us that 3-to-1 ratio as well. And so if we go on to A, what is the probability that the first 5 offspring have small grins and can disappear? So to figure that out, we need to look at what's the probability of getting small grins, which is 3/4. And then the probability of that they can disappear. Sorry, they can disappear is 3/4, and the small grin is 1/4, which will give us 3/16. And the question is asking for the first 5 offspring, so we take this to the 5th. So to the 5th power, which will give us the answer of 0.023% chance that this can happen. And so for B, we are going to go on and, what is that thing called? The binomial expansion equation. And so with that, we're going to put in, and so with that, we're going to be looking for the 5 large grins and 5 large grins that can disappear, and then 3 small grins that cannot disappear. And so for that, our N is going to be 8. So 8 exclamation point over 5, because we're looking for 5. And so we have N, which is 8 minus 5. And so for here, this is the trickier part, where we're going to find what is the probability of 5, which is 9/16. And we're going to take that to the 5th power. And then we're going to find what it is for the 3 out of 8, which is 1/16. And so for that, we're going to put in N, or 8 minus 5 up here. And so for this, it'll give us 0.00077 for an answer, and that's for B. So for C, it's asking us what is the probability that an individual offspring can have a small grin and can disappear, or have a small grin and cannot disappear. So for this, we're going to look at have a small grin, so 1/4. small granted can disappear, so 3/4. I'm going to multiply those together. And so since it's a or question, we're going to add these two things together. It's very important. And then for the next half, it's have a small granted cannot disappear, or 1/4 and 1/4. And so if we do the math on this, it'll give us 1.528 times 10 to the negative 6. And so if we go down to D, oh, just kidding, it's 1/4. That's the answer for the next one.
Spoiler alert.
Spoiler, that's D. So for D, we'll get that answer, but how we get that answer, that's what we're going to talk about. So what is the probability of the first 4 offspring having a large grin and can disappear, and the next 4 offspring having small grins and cannot disappear? So for a large grin, we're going to get the 3 out of 4, and they can disappear, so that's another 3 out of 4. And for the question, it's asking us what the first 4 offspring. So we're going to take this to the 1st to the 4th power. And so we're going to take that times the next set of 4 offspring, which are small grin, which is 1/4, times another 1/4, because we cannot disappear. It is a 1/4 probability or chance of that. And so that's for the next 4 offspring. So that will give us the 1.528 times 10 to the negative 6. And so those are our answers about the Cheshire Cat. That'll take us down to number 4.
Right.
Sorry.
So I kind of don't want to draw out all of these.
For the sake of time, we won't.
Yeah. So I'm just gonna show you evidence of why we think the way that we think.
Oh, these are the pedigree charts, and I would prefer to draw them out. Yeah.
Yeah. It's Friday, so we understand. Okay. So number 4, like we said, it's all the pedigree charts. For number A, we decided that it was autosomal dominant, right? Yeah. So the reasons why we think that is because both males and females show that they are affected here. Oops, my bad. An affected individual will always have an affected parent. So if you could see here, every person that is affected, they have at least one parent that is also affected. The trait occurs every generation, which shows that. So yeah, there's our proof for A. For part B, we said it's Y-linked inheritance because only males have it, and therefore it's only the fathers passing it on to their sons. So that's why it's Y-linked. For C, we decided it was autosomal recessive, and we said that because, where did it go? So the trait tends to disappear in the offspring when an affected person has children with an unaffected person. So there's 2 occasions where there's one occasion where we can see this. In the 3rd generation, we have the 5th person an affected woman has a child with an unaffected male, and we can see that none of their children are affected. 2 unaffected people can produce affected offsprings. So we see that occurring twice. In the 1st generation, 2 unaffected parents have an affected male, and again in the 3rd generation, 2 unaffected parents also have an affected male. So that's why we think it's autosomal recessive. D, we said it's X-linked recessive. We say this because it tends to be that more males are affected than females, and in this chart, it's all males that are affected. And also, the trait can skip generations, and we see that the very last generation, nobody is affected. E, we said it was autosomal recessive. Again, there you go. Because the trait tends to disappear in the offspring when an affected person has children with an unaffected person. We see that in the very first generation, we have an affected mother having children with an unaffected male, and none of the children have it. Two unaffected people can produce affected offspring. We see that again in the second generation. Two parents that are unaffected have an affected male. There's an occasion where it says all offspring of two affected individuals will be affected. It's clearly to see in the third generation. We have both parents are affected and giving it to both of their children, and also inbreeding. Yeah. So that's it for number 4. We move on to number 5.
Oh, sorry. Yeah, I'll go into this one. I forgot to mention earlier, when I was doing number 3 and I was doing the chi-square test or the formula, I had my 6 values here, and we ran each of the values through the chi-square test. And what we're supposed to sum those values at the end to get the final chi-square value. So I just wanted to clarify that. So let's get. So we're going to number 5.
Yeah.
Here we go. Okay. So A, the blank probability rule is used for mutually exclusive events. So mutually exclusive means you're using the sum probability. While the chi-square test compares observed outcome to what was expected. So remember, I had my chi-square test. We're comparing observed to expected using the formula there. So that's the answer. So sum and chi-square for part A. Then for B, more males are affected than females when a trait follows blank inheritance. So if more males are affected than females, it has to be X-linked recessive, because males, if they have one X-linked recessive trait, they're going to express it. Whereas females have the second X-linked X chromosome, which can hide that recessive trait. The other one, while an affected male produces 100% affected daughters when a trait follows X-linked dominant inheritance. So if a father has an X-linked dominant trait, he's going to give that trait to his daughter, and she will express that trait, because doesn't matter what she gets from the mother. If the mother gives her a recessive trait, the father will give her a dominant trait, and that one will express itself. So yeah, it's X-linked recessive and dominant for B. And part C, when calculating the probability, the word or indicates that one would use the sum probability rule. So or means you have two mutually exclusive events, and you have to sum their probabilities to find the total probability that one will happen or the other will happen. Kind of like if you flipped a coin, you said, what's the chance that you'll get heads or tails? Well, when you flip the coin, you're going to get heads or tails no matter what. So it's the sum of both, 50% plus 50%, or just 100%. Yes, that was D. E, when a trait follows blank inheritance, both males and females are affected with the same frequency, and the trait can skip generations. That's autosomal recessive. It just, yeah. No monkey business with sex chromosomes with that one. When a trait follows blank inheritance, affected fathers produce 100% affected sons. So you got a dad got his Y and X chromosome. This one has a recessive trait on it. So his son is going to get the Y gene from his dad. The son has to, so he will have the Y-linked recessive trait all the time, every time. So the answer to that one is Y-linked inheritance. So E is autosomally recessive and Y-linked. And F, sampling error is high when analyzing the inheritance of traits in humans because the blank is typically low. We said that is sampling size because with humans, you can't just take a bunch of humans and force them to take a test. It's not ethical. They have to do it voluntarily. Okay, especially if it's a genetic test, of course. And G, for the purpose of the chi-square test involving genetics problems, the blank equals the number of phenotypic classes minus 1. So that's our degrees of freedom. So, like in my case, I had the 6 possible combinations of phenotypes, and so that's our N. And then we subtract 1 from it, that's 5. That's our degrees of freedom. So, yeah, that's the answer to that. And that's it. Anyone else have anything I want to say?
No.
All right, have a good weekend, everybody. Bye. We're out.